Okay, recording started. Now let me share my screen. All right, so last lecture, we stopped here. So in this example, assume we have 4 individual feeder circuits that's connected with the loads 250 kilovolt ampere, 200 kilovolt ampere, 150 kilovolt ampere, and 400 kilovolt ampere, with the demand factors 90, 80, 75, and 85. So the overall thing here, we can assume you have here a distribution transformer that's converting 33 kilovolts to 0.4 kilovolts. Then there are 4 feeders: feeder 1, feeder 2, feeder 3, and feeder 4. Each one has its own load with demand factor 90, 80, 75, and 85. So the thing you can multiply, or let's calculate the overall load. So basically, calculate the demand, the overall demand for each one. So 250 times 0.9 for the first one, the second one 200 times 0.8, the third one times 0.75, and the last one times 0.85. Then once we do it, the calculation, I think we already have it here, will be as we see in the screen. Then when you sum all of those, there will be 837.5 kilovolt ampere. Now the question is, we need to identify or select what's the suitable transformer ratings if the diversity factor is 1, and the other one if the diversity factor is 1.5. So let's do the calculation. The first one, let's recall the diversity factor. I think this is the opposite. It's the total divided by the max demand. Now, let's calculate the total, and here, which is the diversity factor. The total will be the diversity factor times the max demand. We already have the max demand as 837.5, then times the diversity factor, the total. Then the first case, when diversity factor equal 1, then the total demand will be 1 times 837, so it will be 837.5 kilovolt ampere. The second one, if the diversity factor is 1.5, I believe there's type of mistake, which is basically we need to divide. I think divide by 1. So here divide by 1, and the other one, which is 837.5 divided by 1.5. Then the answer will be 500 something, so which is what we have here, 558, and here 537. Then when the diversity factor is 1, that's what we have, and here when the diversity factor is 1.5. So what we can notice, the main feeder circuit, if the diversity factor is 1, will be 850 kilovolt ampere. However, when it is 1.5, the transformer ratings almost like 600 kilovolt ampere. Here we just approximated. When we approximate it, it will be around this. So as a result, if the diversity factor larger than 1, the suitable value for the transformers will be lower. That's the thing that we need to make sure or to figure out. If the diversity factor is high, it will be better for us. Higher diversity factor leads to lower transformer ratings. That's the conclusion. Let's go to another example. A motor that are working 8 hours a day, 50 weeks a year. So the annual operation, 2,000 hours. It's working 2,000 hours per year. 2,000 per year, hour per year. Then we need to calculate the utilization factor. The utilization factor, which is basically how much is working hours divided by the hours per year. How many hours per year? 24 times 365. This yields to 8,760. then the answer will be the working hours, 2,000 divided by 8,760. So it will be 22.83%. This is the utilization factor. Utilization factor, which is basically we are using only 22.83% of hours through the year from the motor. So which is very low value. Then um, we can let the motor working extra hours. Then we have more room for the motor to work extra hours. That's the point. Another example, assume at the load, we have a 240 volts single phase shower heater, 8 kilowatts, and we have a unity power factor. Let's calculate the currents, then we can calculate the suitable circuit breaker value. So as we know, in our home, we have a breaker panel. So there is a circuit breaker for each room, a circuit breaker. One of them, for example, there's a circuit breaker, 20 amps, that can be used for lights, or maybe we have 15 amps also for lights. We have maybe 30 amps for sockets, and we can have maybe 50 amps for large applicants. Then when we look at these breakers, um, we need to select which type of circuit breaker that I need to install for the shower heater that I have. Then from the data sheets of the shower heater, it says the amount of power, 8 kilowatts. That's from the data sheets. And the other thing related to the currents, or not the current, the voltage. The voltage, it's supposed to be 230, but I'm just gonna assume it's 240 volts. But actually, again, it's 230. In Jordan, 230 volts. So again, assume it's 240. Then we need to calculate the currents. As we know from the circuits class and from the power class, that the complex power S equal P plus JQ, and it can be S angle theta. P is the real power, Q reactive power, S is the apparent power, theta is the power factor angle, and it is the same as V times I conjugates. Then we can say it can be V times I cosine theta plus V times I sine theta, or in rectangular coordinates, V times I angle theta. Then, since the unit is in kilowatts, the real power kilowatts, reactive power var, apparent power volt ampere, complex power volt ampere, so the units that we have in watts, they are in watts. Since they are in watts, this means it is a real power. Then the real power formula is this one. So what we will use is this formula, P equals V times I times cosine theta. And as we know also from circuits and power classes, that there is something called power factor, which is the cosine theta. Then, in other words, we can say P equal V times I times the power factor. Our target is to calculate the currents. So we can say I equals to P divided by V times power factor. Substitute the values. We have the P, 8,000 watts or 8 kilowatts, 8 times 10 power 3, divided by 240 times 1. So the answer will be 33.3 amps. Then you can say we need to use a circuit breaker. We need to use a circuit breaker, which is in shortcut CB, means circuit breaker, with higher ratings or more than 33.3 amps. So you can say, for example, we can select, for example, 40 amps or select 50 amps, depending on the availability. Okay, so that's a very important application to make sure that we need to select the suitable circuit breaker, or assume that you already purchased this new shower heater and you need to install it at your home. So if you need to install it at your home, you need to make sure to connect this heater to the suitable circuit breaker. Then you can say, okay, do I need to install it to the same, for example, like bathroom breakers, or do I need to install a new line or a new circuit breaker, or do I need to replace the existing circuit breaker with another one? That's something that we need to take into consideration. Then the first thing, again, calculate the rated current. Make sure that the circuit breaker is capable of handling these currents. Okay? The other thing, um, assume we have a ring circuits, and there we have a 15 sockets, 30 amp sockets. So the maximum thing, 15 socket times the rated 13 amps, which is 195 amps. But the thing in real life, these 13 sockets or these 15 sockets may feed a lamp with a 60 watts, or it can feed a cell phone charger with 20 watts or 25 watts, or it can feed a washing machine, which is 3 kilowatts. So I would say not it all of 15 machines, they won't work, or they won't work on 13 amps rating. It's not necessarily all of them will be working on 13 amps. Maybe socket number 1 can work with 1 amp. Socket number 2, it can work with, for example, like half amps. Number 3, 2 amps, and so on. So as a result, we realize that 32 amps is enough. That's a case study. So we can say, yes, we have 32 amps rating, but the overall, when you sum all of them, 195 amps. So you can calculate the diversity factor as 195 divided by 32, then it will be very large value. So the thing here, we need to make sure we have a diversified loads. And the other thing, which is not all of the sockets will be at their max. That's something that you need to keep in mind. Sometimes you can connect them to the computers. So when you connect the group of computers, the computers will not consume 30 amps, of course. And sometimes you can consume it, connect it to the washing machine, and it might not consume that much, etc. It depends. So there is a diversified. Therefore, here in this case study, we realize that 32 amps is more than enough. The other thing,
Yeah,
there's...
I have a
Yes,
question.
of course.
It's not on this example, just a general question. Like, let's say if we have a device that consumes about 30 amps, would we choose? We can't choose a 30 amp circuit breaker on it, right? Because it would trigger the circuit breaker.
Yeah, so yeah, the thing about it, here there is a breaker panel. Then from that breaker, it will go to a room. That room has 15 sockets. So all of them, they are connected to the same breaker. 1, 2, 3, 4, until 15. So we don't want to make a single breaker for each one. It will not be feasible. So we will put all of them in one breaker. That breaker, for example, it can go to and here's the main circuit breakers. And there's a breaker that goes to, for example, let me call it, this is a living room. So that living room has 15 circuit breaker, but that 15 circuit breaker, they are not necessarily to be all of them taking 30 amps. So that socket can handle 13 amps, but it's connected to the TV. The other one is connected to the router. The other one to the lights. Then there's another one to, for example, cell phone charger, and so on. So you can see all of them are light loads. I mean, the socket itself can handle up to 13 amps, but they are not working as a 13 amps.
Yeah. What
Maybe
would happen
another one.
if
Yes.
what would happen if we exceed like this socket that would only handle 13 amps? What if we exceed 13 amps? Like let's say 15, and it doesn't really have
Okay.
individual circuit protection.
Yeah, there should be a fuse inside the socket to protect this. So if it is more than 13 amps, the socket start burning, or it will be heated, or there will be should be a fuse. If there is no fuse, it will start burning, which is something, yes, of course, something dangerous.
And is there like specific tolerance, like 13 amps, 13 amps? What if you go like 13.1 or 13.2 amps? Like what's
That's a good
the
question. 10% tolerance
person?
and 10% with 15 minutes duration. We can say 15 or 20% with 5 minutes. That's a good question. Yeah. So there's a tolerance, depending on like the duration, of course. And of course, like if you make it 14 amps, even for a long period, it's not only 15 minutes. If you make it 1 amps increase, I do think there will be something. But I mean, just for safety, why? What's the point of making that number, specific number? Because when there is a high load, there will be high heats. So there will be some losses, there will be some high heats. This will impact the physical equipments. So if you exceed, for example, 20% more than 5 minutes, that material start melting, which will make a permanent damage. That's why we say like 10%, 15 minutes, 20%, 5 minutes. So if you exceed this, it will make a permanent damage, or maybe we have a fuse. It depends. So I would say in some modern sockets, there are fuses, but in the old fashioned, there is no. It will cause some damages into the socket itself. So it will no longer conduct electricity. Then you need to replace it with another one. Unless if that amount of current is very high, reach 32 amps, the overall system, then the circuit breaker will trip. Okay?
Yeah, thank you.
You're welcome. Now, let's go to something else, which is the customer number. Assume the following scenario. This is the transformer that's converting 132 kilovolts to 33 kilovolts. Now, we have several feeders, feeder 1, 2, 3, and 4. So let's assume this is, for example, like Madab substation. Then feeder number 1 goes to the old city. Feeder number 2 goes to American University of Madaba. Then feeder number 4 goes to, let me assume, German Jordanian University. It's not only going to this university, it's going to several things. Then that feeder goes toward that area. Then we have laterals. I mean, this feeder is not associated with that, with the only just the university. It goes to the nearby, to the neighbors, not only to our main campus. It goes to different several neighbors. Then from that, there will be some laterals. Laterals in Arabic is called tafri'a. So just like go lateral to several things. So that lateral number 1, lateral number 2. So you can see the feeders, we call them F. F1, F2, F3. So let's focus on F4. Then in lateral, we call it L. So L1, L2, L3, L4. So let's focus on, for example, L2. Assume L2 or lateral L4, 2. 4 associated with feeder, L with lateral 2. Then lateral 2, this is the one that goes to GJU. Then that lateral, it goes inside the campus, inside the university. Then we are inside the university. We need to have a distribution transformer that's converting 33 to 0.4 kilovolts. So each dot means a distribution transformer. A distribution transformer. Let's assume the dot number 7, or the distribution transformer. It's called distribution transformer. As a shortcut, we call it DT. DT, the dot number 7, count them, it's number 7. This is the one that goes to C building, which is the engineering building. So we can say, we will call that distribution transformer as DT427. 4, feeder number 4. 2, lateral number 2, the one that goes to GJU. 7, the transformer that goes to the C building. Okay, then from that feeder, we have several customers. So the customers, we have customer 1, 2, 3, 4, 5, 6, depending on the customer. We can say like the floors, floor number 1, floor number 2, etc. Then we call it, this is the customer. And the same thing, maybe you can apply it for the homes. So your home, you have, a counter meter that, or the meter, there's a meter number for the, there's a number on the meter, and that meter, we can make a projection for it, so as a customer number. From the customer number, there are several numbers like 4276. We will say it is in feeder number 4, lateral number 42, which is feeder 4, lateral number 2, distribution transformer number 427, and the customer number 427, and customer number 6. That's the thing. So here, this is, a code to know where's your location. So for example, if there is a power outage at home number 4, so homework number 4 will call the power company and call the maintenance, or call the emergency. There is a power outage at my home. So they will they will ask him, where's your location? Give us your meter number. So when you give them the meter number or the counter number, they will go to the, because they are masking the number, so they will make a lookup check. Then they will say, okay, this is the customer number. The customer number, which is 4274. Then they will send the maintenance team, go to this number. So the maintenance will understand, let's go to feeder 4, lateral number 2, distribution transformer number 7, home number 4. That's how they understand it, and they will be easy to locate where is the problem. They will be easy to locate where is the customer location. Okay? So the customer number, it's something important for us to identify where is the location of the customer, or where is the location of, there is, for example, the distribution transformer. If there is something wrong in a certain distribution transformer, they will label it as, okay, go to label, do DT427, do a maintenance there. That's how we do the numbering. Okay, any question? All right. Now, the next thing, we will go to the electric billing and tariffs. Here is the rated schedule in the United States. This is from the textbook. In the United States. So in the United States, it depends. There is a minimum charge. Like first 20 kilowatts will be $2.25 per month. I think this is very old because it's so cheap. Very old. Right now, it's way expensive, more than that. Of course, it's not 2.25 for first 20 kilowatts. Anyway, this is very old ratings. Anyway, which is $2.25 per month. This is a fixed charge. Then the next 80 kilowatts, $0.0355 per kilowatt hour, and so on. So there it is. We call it levels, depending on the level. Where is it located? So we can say here, depending on the tariff, depending on the amount of consumption, you can make the calculation. For example, like you can assume you are consuming 60 kilowatt hour, so you can divide it as the first 20, which is 2.25, plus the 60 minus 20 will be 40. So plus 40, we are still within this level, then it will be 40 times 0.0355. This is, which is called how you can do the calculation. And so on. If it is 100, you can do the calculation. If it is 200, 400, etc.
Is it a
yes.
bit counterintuitive for it to decrease with the more electricity you use, not increase?
Yes, that's something interesting. That was old in the United States. Right now, I think the situation is different because they are forcing the people to try to reduce their billing. And again, it depends on the state, depending on the company. As far as I know, I've been, for example, in Alabama. They have a fixed rates, I think, I believe $35 as a fixed charge. That's why I said it's too old. After that, I believe there is a 12 cents per kilowatt hour. No matter how much power you are consuming, it's 12 cents per kilowatt hour. So this is different. I'm talking about, this is a rates in the textbook. But I mean, I would say in real life, it's not like that. I mean, I believe right now they're modifying this. And again, depending on the policy, depending on the states, even in the same state, it depends on the power company. I mean, Alabama Power different than, for example, the Georgia Power, different than the Southern Company, etc. Here is, I mean, another rates. I mean, there is something we call environmental subcharge, fuel cost adjustment, sales tax, total amount, etc. So this can be kind of different depending on, I mean, several factors. So there should be regulations by the power company and by the government to tell you about the tariffs. Okay, here is also the tariff for commercial areas. The commercial can be different because in commercial you will pay more money, while in the residential pay less money. And the other thing, there should be power factor coefficients, power factor penalty, depending on that. And the other thing related to the commercial, there should be something we call it on peak and off peak, while we are not seeing this in the residential. What do you mean by on peak and off peak? So on peak, whereas there is a high demand of power and we need to reduce it, therefore it will be more expensive. While off peak should be cheaper because off peak, the power consumption is low, then it can be fine. Here, in this example, we see off peak season during, or on peak season during the summer, off peak during the winter. What's the point of this? Why they are using this? Because during the summer, there will be a lot of heat. The weather is heat. It's so hot weather. So the hot weather will impact the physical components for the power system. Then the power system components or the electrical system components cannot be loaded in their rated value because, for example, it can handle. For example, the transformer can handle 90 degrees Celsius, but the weather is 40 degrees Celsius comes from the weather, not from the load. So the 40 to 50, the change will make the loaded for the transformer low. We cannot load it high as in the winter because the winter can reach up to 10 degrees Celsius, and we have enough room from 10 Celsius to 90 Celsius. We have enough very large value, then during the winter, we can put more loads on the power lines and on the transformers. So as a result, in the summer or in the winter, we can put more loads on the power lines, while in the summer, no, we couldn't. That's why sometimes, even like in Jordan, we have the energy crisis or the energy problem and overload during the summer more than winter. Because the winter, again, we have enough room to do that. Now let's talk about Jordan. Jordan, as we know, there are two types of tariffs. There is the supported tariffs and the unsupported tariffs. So the unsupported tariffs, we started this, by the way, in July 2024, last couple of years. The unsupported, some people say it's very expensive because when you, between 1 to 1,000 kilowatt hour, it will be 120 fils, while if it is more than 1,000 kilowatt hour, it will be 150 fils. While the supported tariff can be like this. The supported tariffs, which is between 1 to 300, will be 50 fils. 301 to 600, 100 fils. More than 600, 200 fils. Compare it with the supported one. Supported and supported. Here, 1 to 300, the supported, which is 50, the unsupported 120. 300 to 600, the supported one, 100, here, still 120. 600 to 1,000, this is 200, this is still 120. 1,000 and more, this is 200, this is 150. So you can notice during the first part, the supported one is cheaper, right? During the second part, the unsupported is cheaper. So the thing, it's not necessarily using the supporter does not mean that this is the most economical, this is the most beneficial one. Okay, sometimes it's cheaper for you to move to the unsupported one, so you will pay less money. Yes, that's true. Yes, that's true. So as a result, I'm gonna assign a homework for you. That homework submission is due to next week, on Thursday. Yeah, we can say due to Thursday or Tuesday. Homework. I'm gonna put the homework information on Microsoft Teams, but the submission will be on e-learning as a PDF file. That homework, go to your utility bill and recalculated it. Recalculated it based on the first thing, supported tariff and the unsupported tariff. Then after that, I need you to see which one is cheaper for you. You need to answer this, which one is cheaper. After that, I need you to answer this, when the supported will equal to the unsupported. So the overall trend for the energy, the supported is cheaper. Let me say, here is the cost of unsupported. Here is the cost of supported. Here is the cost of supported is cheaper, until reaching the points where they will equal to each other. Then after that, it will be more expensive. So here is supported. Here is unsupported. Therefore, there will be a certain level where the supported equal to the unsupported. This will call it the threshold. At the threshold, we can say, if you are consuming power more than this amount of kilowatt hour, or more than this amount of money, if your energy bill more than this amount, then switch to the unsupported. It will be cheaper for you. Don't stay on the supported one. So this threshold must be calculated. I need you to calculate it. By the way, it will be around 120 GDs. Something around that, 120, 115, 110, something like that. You can calculate it, but it will be around this value. So as a result, let's assume it is 120. Then look at your utility bill for the last 12 months. If all of them more than 120, all of them, then I recommend you to remove the support. Move to the switch to the unsupported tariff. It will be cheaper for you. While if the vast majority below than 120, and maybe just 1 month it goes up for a reason, then after that, the rest below than 120, stay on the supported tariffs. Okay? So this is your homework, and I will mention details about the due dates after the end of today's lecture. Then the submission will be 1 week. The submission will be on e-learning, submitted as a PDF file. So what you need to do is the submission, submit the first thing, your utility bill. The second thing, a screenshot of your utility bill. The second thing, your calculation. Calculate the supported tariff. Then the unsupported tariff, which one is cheaper? Where is the threshold? When we will reach this threshold? Okay. Now let's keep going. The second tariff, which is basically the customers, like, for example, like the worship places, the government places, the gyms, etc., the charities, where they are not considered as a commercial. They are not commercial, but we call it they are charity, like hospitals, worship places, gyms, not the private gyms. I'm talking about like the gyms, or I would say like the sport clubs, etc. The charities, all of them, they have this type of rated, the tariff. That's their tariff. And the other thing, the commercial tariff. And this is the industrial tariff. Also, you can see the industrial tariff, there's a power factor penalty. If the power factor below than 0.88, then there will be some penalty. You need to pay some penalty. If it is more than 0.88, nothing. If between 0.88.7, it will be 0.77 times every 0.01. So there will be there will be 2 meters, a power meter, and there is power factor meter. Those in the industrial loads. So the power factor meter, if it goes below than 0.88, then there will be a big penalty. So even like if the power factor very poor, below than 0.5, then it will be 1.5 times 0.01 times 0.8, which will be very large value. So here, the people or the company or the industrial loads, they will be forced to improve their power factor, so they will not pay the penalty. So this is called power factor penalty. Power factor penalty. This is only in industrial loads, not in the customers, not in commercial, not in residential. Industrial loads. Why? The industrial loads, the vast majority of the industrial loads are based on motors. Motors, they have inductance, equivalent circuit inductance. Inductance means consuming a lot of reactive power, consuming Q. The power factor, as we know, which is P over S, or which is P over the square root of P squared plus Q squared. So if Q goes high, what will happen to the power factor? Will be low. How can Q goes high? If you are turning on a lot of motors. Turning on a lot of motors, it will cause a poor power factor. Then they will pay a penalty. How can I solve this issue or remove this issue? You can solve it by installing capacitor bank. So capacitor bank is basically the purpose of that. It will increase the reactive, add more reactive power. Let me say it again. The capacitor bank will supply reactive power. So the Q equivalent will be the Q of the motor minus Q of the capacitor. So as a result, we can say the power factor will be P divided by square root of P squared plus Q motor minus Q capacitor squared. Then definitely it will be improved. Here is the power factor. Then it will improve the power factor. That's what we are doing. That's why we are adding capacitor bank. This is something undesired and we don't want this to happen. Okay? Any question about the tariffs?
Yes. What about the agricultural sector? What if somebody like has a huge farm that has a lot of motors? Why don't they get penalized?
It depends on the load, like the agriculture. If it is a small motor, small water pump, there is no problem. But if it is a very big water pump, commercial, it will be considered as industrial, not commercial. Commercial, what I mean by commercial, which is basically like the malls, the supermarkets. That's what I mean by commercial. But I believe the agriculture, it can be kind of industrial local. They will be treated as industrial loads. Okay.
Yeah, got it.
All right. So any other question? Okay, so don't forget, like there will be a homework on the utility bill. Now the next thing is the Jordanian electricity sector. I think let's pause here, then we will continue on that next lecture. Okay? So let me stop here. I will stop here. Next lecture, we will talk about the Jordanian electricity sector. This is a very important topic, and I believe everybody must know how is the electric system in Jordan. But the overall here is like about the companies, Ministry of Energy and Mineral Resources, which is called MIMR, the National Electric Power Company, GIPCO, Jordanian Electric Power Company, IDCO, Erbil District Electricity Company, and IDCO, Electrical Distribution Company, etc. Again, we will talk about it next lecture. Okay, now any question about today's class, today's lecture? Right, let me stop the recording.